All right, so in this lesson, we actually want to revisit something we talked about briefly here a little while ago, but just practice it a lot more than we did before. And that is this first derivative test. Okay? Now, you see some pictures here. Okay? But let's state what the first derivative test is. Okay? The first derivative test says that if f prime of c equals 0 and f prime of x is less than 0 for x is less than c, and f prime of x is greater than 0 for x is greater than c, then there is a what? At
plateau.
If the derivative is negative to the left of c and positive to the right of c,
There's a limit.
then what is there at c?
Minimum.
A relative minimum. Okay? There is a relative minimum at x equals c.
I thought this was a description of the derivative.
Well, this is our first derivative test. Okay? So that's this case right here. Notice to the left of c, our derivative is negative. Okay, because the slope of the tangent line is negative. To the right of c, the slope of the tangent line is positive, so the derivative is positive. Therefore, at c, there is a relative minimum. Okay?
F prime of c doesn't have to be 0. It can be like...
No, it does have to be 0.
Okay.
Okay? In order to determine that it's right there, the local min or local max will only occur at a place where the derivative equals 0.
If it's differentiable.
Okay?
Right.
Yeah, well, if it equals 0, then it is differentiable at that point.
Oh,
Okay?
I think we have done something like this before.
Yes, we have. We're just revisiting this. We're coming back to it, looking at it a little bit more closely this time and doing some extra practice. Okay? So here we have a relative maximum. I'm not going to write this whole part out, but there's two other parts to this as well. All right? The second part is right here. We have a relative maximum if the derivative is greater than 0 to the left of c, and it's less than 0 to the right of c. Okay, so if the derivative is positive here and negative over here, then c is a local maximum. Okay, but then you have a third case, and that is when there is no change in sign. Okay, so f prime of c still equals 0, but there is no change in the sign of f prime of x. Okay, so you'll notice here positive and positive. Okay, positive and positive. No change of sign. It is not a relative min, nor is it a relative max. What do we call that?
Plateau.
That's a plateau.
Can't you call the relative min and relative max a plateau too?
No.
No.
A plateau, those are min and max. A plateau is when you're going a certain direction, you level off, but then you continue that same direction. Okay?
If you had like this.
So here for another plateau, if we are decreasing, or the derivative is negative here, and it's negative over here, no change in sign, it is a plateau point as well. Okay? Now there is a term here, strictly monotonic. Mono meaning one, yeah.
Like one direction.
Like monotonous, okay?
What does that mean again?
That just means like boring, one the same, okay? It's strictly monotonic if on an interval, if it's either increasing on the entire interval or decreasing on the entire interval. In other words, there are no changes in direction.
But like a sound, like a voice, is like monotonous. That's like the same all times, right?
Yeah, it has one level of sound. It never changes pitch or anything like that.
Okay, that makes sense.
Monotonous, mono. So here it's monotonic. It doesn't change sign. Okay. It's constantly increasing on the interval or decreasing on the entire interval. We would say it's strictly monotonic. So that's just a term I want to be familiar with a little bit. Okay. So this rule, this first derivative test, is what we use to find relative extrema. Now notice we were looking for absolute extrema, and we said on an interval, and we said sometimes you could have relative extrema that were also absolute extrema, okay? But you would only ever have one absolute extrema unless two things had exactly the same value, all right? You can have multiple relative extrema, okay? Now, let's look at this problem. I want to step you through the whole process here of how you would determine whether you have a min, a max, or so forth, okay? So, for this example, I'm going to find our derivative first. So f prime of x equals 3x squared minus 3x. Okay? If I were setting this equal to 0, I'd factor out the 3x and I'd get x minus 1. Okay? So I would get here x equals what?
1 and 0.
Yeah, 0 or 1. Okay? Now, you'll notice this little table. This isn't always going to be given to you. Alright? But let's look at what we've got here. Okay, we've got x equals 0. And we've got x equals 1. Now, those two values are going to give us either a max point, a min point, or a plateau point every time. So, notice the intervals that we're looking at, okay? We have an interval from negative infinity up to 0. Then we have the interval from 0 to 1, okay? And then we have the interval from 1 to positive infinity. Okay? Now, we're not going to use every box in this little table, and there are other ways that you can do this, but this is just one way. All right? So, what we want to do here is pick a test value that's in this interval. Okay? So, what value do you want to use?
-7.
Okay, -7. Now, we're going to test that in what? The function or the derivative?
Function.
The derivative, because that's the value that we really care about, right? So we're going to pick x equals -7. So I'm going to do f prime of -7. And you'll notice, let's see what we get. We get a -21 times -8. So in that interval, our derivative is positive. Okay?
I think it's 168.
F prime of x is positive. So that means that it is increasing, right?
Yeah.
So now let's do the same thing for the interval from 0 to 1. Question?
What if when x equals -1, the function slightly decreases, then increases again, the slope? The function does something like this.
Well, that's the thing. It won't, because in order to do that, you would have to have another value where the derivative equals 0.
Okay.
Okay? That's why we identify those zeros first for the derivative, because I know everything to the left of 0 is going to have the same sign for the derivative.
Mhm.
It may be a little flatter or a little steeper, but it will all be positive.
I don't understand.
Okay? Mm-hmm.
So why do you do the test value if you already know that it has to increase to go from negative infinity to 0?
Well, no, x is increasing, but we're talking about what the derivative is doing. Okay?
Mhm.
And if the derivative is positive, that means the function itself was increasing.
Oh,
Okay?
understood.
All right, so now for the interval from 0 to 1, let's use half. So f prime of a half, that's going to be 3/2 times 1/2 minus 1.
0.75 negative.
Okay, it's going to be negative. So f prime in this interval, f prime of x, is going to be less than 0. It's going to be negative. So what's my function doing? Decreasing. So what do I have at x equals 0?
Relative max.
It's a relative max at, and this is the point 0 what?
-1. No, just 0, 0, I think.
0, 0. Plug 0 into the original function and you get 0. So this is at 0, 0. There's a relative max at 0, 0.
So you plug 0 back into the original function?
In the original, well, we're looking for a point on the graph, right?
Yeah.
To get a point on the graph, you got to plug it into the original function.
Good.
When we're talking about directions, we're using the derivative. When we're talking about points, we're plugging it into the original function. Mm-hmm.
Could you do, I wouldn't do it because it would take more time, but could you find if the derivative, the slope is increasing or decreasing by not finding the derivative, but by finding y values for 2x values?
Technically you could do that,
But it's not as possible.
yeah. All right, so then what would we plug in for the last interval? What do you want to use?
7.
7, okay, so f prime of 7.
Why don't we use 2?
We could use 2. We could use anything as long as it's bigger than 1, right?
Let's do 7.
So 3 times 7 is 21 times 7 minus 1.
Bigger than 0.
Good, it's bigger than 0. We don't care what it actually equals. All we care about is the fact that it's positive.
Very minimum.
The screen is
Okay? And you're right, since it's changing from decreasing to increasing, okay, it's greater than 0. Since it's changing from decreasing to increasing, we do have a relative min at the point 1, and what would that be?
-1/2.
Yes, -1/2. 1 minus 3/2 would be -1/2. Okay? So, finding intervals of increasing or decreasing. Here's the basic process, okay? And this is, this is kind of an extension here of our first derivative test, okay? If f is continuous on the interval from a to b, to find the open intervals on which f is increasing or decreasing, use these steps. First of all, locate any critical numbers, so not just where the derivative is 0, but also anywhere it's undefined. Okay, that was a polynomial. We know it's continuous everywhere, so we didn't have to worry about that on the previous example. But locate all critical numbers. Use these numbers to determine your test intervals. Okay? Then determine the sign of f prime at one test value in each of those intervals. Okay? And then, based on that sign, determine whether f is increasing or decreasing on each interval. Okay? So determine if you have a relative min or a relative max, or is it monotonic? Okay? If you don't have any change in sign, you would say it's monotonic. Okay? So we've got a couple of other examples here. I want you guys to take some time here to work on these, just for some extra practice. So let's look at this first, this example number 2. We're going to find the relative extrema of f of x equals 1/2 x minus sine of x in the interval from 0 to 2 pi. Now, you can see the graph over there. You're not going to be given the graph on these, okay? So you can see that we ought to end up with one relative minimum point and one relative maximum point, just from looking at the picture. But let's look at this algebraically and go through the process of finding it, okay? So what is the first thing that we're going to do when we're trying to determine intervals and all of that? Find the derivative of the function, okay? So, if we go through and we find f prime of x, what's that going to equal here? 1/2. Good, 1/2 minus cosine x. Good, Terry. Okay? So 1/2 minus cosine of x. And then what do we do with that? Very good. We're going to set that equal to 0 and solve it. Okay? So this isn't too hard to solve. We have cosine x equals 1/2, and from your unit circle, you guys know that x equals pi over 3. Pi over 3 and? It's still got to be a pi over 3, right? It's something pi over 3. 5 pi over 3. Hey, don't be surprised if you guys have a pop quiz at some point on your unit circle. It'd be a shame to learn all this calculus and then fail the AP exam because you don't know your unit circle. Okay? They expect you to know it real well. Alright, so I've given you a table here. I want to show you how you can use this table. There are a variety of ways that you can do this, but especially here beginning, this table kind of helps us structure things a little bit. So what I'm going to do is, these are our two critical numbers. I don't have any values in this range from 0 to 2 pi where this is undefined. So these are the only two critical numbers. And what I'm going to do is I'm going to put them here. X equals pi over 3 and x equals 5 pi over 3. And the other three columns I'm going to use for the different intervals that these have defined, okay? Because I'm on the interval from 0 to 2 pi. Here I have the interval from 0 to pi over 3. Okay? All right, so from the left side of my interval up to my first critical number, is my first subinterval, you could call it. Okay?
It's not a bracket, right?
It's just parentheses, because at pi over 3 it equals 0. Okay?
So is that an interval? So that's like a point.
No, that's an interval. The interval from x equals 0 to pi over 3.
Oh, it's not including that.
Not including pi over 3. So then this is where it equals pi over 3. And then the next interval goes from pi over 3 over to 5 pi over 3. And then the last one goes, once we pass 5 pi over 3, up to 2 pi. Okay?
What if something's already over 2 pi?
What?
What if a number is already over 2 pi?
That's okay. Can happen.
I mean,
Oh wait, if one of your critical numbers is bigger than 2 pi, you would just ignore it then. You would only look at the ones that are within the interval that you want.
okay.
And you know this is a periodic function, so technically it would go on forever in both directions.
Okay.
So that's why they had to give us an interval for this one. All right, so at this point we need a test value, okay? Now, we're not going to use all 3 boxes underneath all 5 columns, okay? We're only going to use some in some cases. The test value, we're going to pick a number in each of these intervals, okay? You typically try to pick ones that are easy to work with. So like here, from 0 to pi over 3, I'm going to pick one of the angles that's on the unit circle.
Pi over 6?
So, okay, let's use pi over 6, all right? So we're going to use pi over 6. We're going to let x equal that. And what's the sign of the derivative? Well, the derivative is 1/2 minus cosine of x. All right, so if I'm doing, actually, let me erase this a little bit. I'm going to go ahead and say I'm doing f prime of pi over 6. So that's going to be 1/2 minus, what's cosine of pi over 6? Root 3 over 2. Okay? Now, I don't care what it equals. All I care about is the sign. Is this positive or negative?
Negative.
It's negative. So, what can I tell about f in this interval? It is decreasing. F is decreasing. Good. Okay? Does everyone understand what I did here? Now, we need to do this for all 3 of these intervals. Okay? So, someone give me an angle between pi over 3 and 5 pi over 3.
Pi.
Yeah, there we go. Pi. That'll be easy to work with. So f prime of pi. So we have 1/2 minus, what's cosine of pi? Negative 1. Negative 1. So 1/2 minus a negative 1. Positive or negative? It's positive. So my function is doing what here? Increasing. Now that we've said that, we can come back here and say, hey, what's happening at pi over 3? We have a relative minimum, and that point is pi over 3. And let's see, it would be sine of pi over 3 is root 3 over 2. This is pi over 3 times 1/2, so that's pi over 6 minus root 3 over 2, which,
And how do you get that?
I just plugged it in to the original function. Okay? And you could leave it like that, or you could give it as a decimal. If you had to actually graph it, you might want to give it as a decimal. But that's where your relative minimum is. Okay? So now we just need to do our last interval here. Okay, what's an angle between 5 pi over 3 and 2 pi? What's that?
3 pi over 2.
3 pi over 2 is smaller than 5 pi over 3.
So 11 pi.
Or wait.
Yeah, 11.
No. Hang on. 3 pi over 2, that's 1.5. This is 1.4. That would work. Sorry. 3 pi over 2. Okay. Yeah. Yeah. Okay. Sorry. So now that's 1/2 minus cosine of 3 pi over 2 is 0. So that's not right.
It's minus, it's not time. It's minus.
Yeah, it's minus. Hang on. 5 pi over 3.
And 6.
No, that's not 1.4. I was thinking. Hang on. This is bigger than 3 pi over 2. We can't use 3 pi over 2. We're moving too fast. Let's pick a different angle. Sorry. 11 pi over 6. That one will work. That one definitely. 11 pi over 6. There we go. So we have 1/2 minus cosine of 11 pi over 6. Same thing as cosine of positive pi over 6.
1 over
Root 3 over 2. Okay? So is that positive or negative? That is negative. So our function is?
Negative.
It's decreasing. Our function is decreasing when our derivative is negative. So that means this point right here at 5 pi over 3 is what? That's a relative max. Okay? Relative max point. Okay? So that's at 5 pi over 3. And then we could figure out, okay, this is going to be 5 pi over 6 minus, what's the sine of 5 pi over 3?
1 over 2.
In the fourth quadrant? So sine is negative, so this is plus 1/2. And again, you could get that as a decimal. Okay? Again, just plugging that into the original function. Okay? So it's minus a negative 1/2, so we have plus 1/2. Okay? All right. So that's the process that you have to go through. And you can see here that matches what you can see on the graph that was given. All right? We have a relative min. That was at pi over 3. The relative maximum is at 5 pi over 3. Notice here we are decreasing, then we are increasing, and now we are decreasing again. Okay? So this is just kind of a confirmation of what we found algebraically. Okay? All right, now example 3, we got to remember that not only are our critical numbers where the derivative equals 0, but it's also where the derivative is undefined. Okay? So for this one, we'll only be able to identify the critical numbers on this one. We won't be able to do the entire table, but what is our derivative for f of x here?
2/3 x squared minus 4 -1 to -1/3 times 2x.
So the negative 1/3 times 2x. Good. Okay. Now, let's simplify this a little bit here. We have 4x over 3 times the cube root of x squared minus 4.
Wait, where did the 4?
because the 2 from the 2/3 and the 2x from here. Those are the only things in the numerator. The 3 and the x squared minus 4 to the 1/3 go to the denominator. Okay? So, what would make this either equal 0 or be undefined?
X equals 0, -2, +2.
Okay, x equals 0 would make that equal 0. But also, these are our critical numbers. X equals 0 makes it equal 0, but also a positive or -2 would make the denominator equal to 0. So that would make it undefined. So here we have 3 critical numbers, all right, which our table, we need like one more column for our table here, if we're going to do the whole thing. So we've got 0, we've got x, or wait, I should start with -2, because you want to go smallest to largest. So -2, then x equals 0, and we'll just split this one in half.
Wait, why don't you start at
Yeah.
the first column?
Well, because we need intervals too. Okay.
But they didn't give me an interval. How do you know what intervals to use?
Okay, that's a good question. So we're going to go everywhere from the left, so -infinity up to -2. And then the interval between -2 and 0. The interval between 0 and 2. And then the interval from 2 to +infinity. Okay? So there we're going to have 5 different intervals that we would need to test. Okay? And then we could do the same process. So you're testing these 5 intervals. Once you get these 2, you'd be able to tell if -2 is going to be a min point, a max point, or a plateau point. Once you do -2 to 0 and 0 to 2, you'll be able to tell if there is a minimum point, a maximum point, or a plateau point here at 0. And so on. Okay? So you just fill out the rest of that table.